We are going to talk today about neutralization reactions. And think about what the word neutralization means. Okay? If you neutralize something, you're going to make it ineffective, right? If you, the word neutral, you think about in terms of pH, you think about pH of 7, meaning it's not acidic, it's not basic, it's been neutralized. Well, with neutralization reactions, think about what you could do. You have an acid. What do you think you could mix that with to make something neutral? All right. What would offset an acid? Hopefully think maybe a base. And so a neutralization process is where you take an acid and a base and you mix them together. And then you can neutralize, if you do the right ratios, you can neutralize the pH of your solution. So when you do this, you actually make salts. So think about salts: sodium chloride, magnesium chloride, potassium chloride, metal, and a non-metal are your salts with an ionic compound. Sometimes it's in metal and a polyatomic ion as well. Instead of just a non-metal, you have a polyatomic ion. But I want to show you how a salt is formed when you take the anion. Now remember, that's the positive charge of an acid, so like HCl, okay, the anion, and then you take the cation of a base and combine those, all right, and those produce salts and water as products. And I think I just said something that I didn't mean to say. I think I misspoke and said the anion was positively charged. That is so wrong. So an anion is the negative ion of the base, and the cation is the positive ion of the base. So anion of the acid, cation of the base. So anion is the negative ion of the acid. You take the positive ion of the base and you combine them. That's how you get a salt, and that's how we neutralize a reaction. So let's take an example of one. I'm hoping you're looking at this and you see that magnesium hydroxide is the base. Now, how do I know it's a base? Well, I look and I say, first of all, there's no proton for it to donate. And then it has this telltale hydroxide ion there. So those two things, there's no proton to donate, so it can't be an acid. And it has this OH grouping, which tells me it's a base. I'm going to react it with HCl. Now, this is the acid, and I know that because it's got this proton right here that it can donate. Now, basically what you have happening is a double displacement reaction where two things, in this case, is going to be hydrogen and magnesium, switch places. And what I mean by that is when you react this base with this acid, you get a salt, magnesium chloride, salts are neutral, and you get water. And water is neutral. So you mix in the right proportions, magnesium hydroxide and hydrochloric acid, with the balanced reaction. Notice the coefficients. You have 2 moles of hydrochloric acid for every 1 mole of magnesium hydroxide. And when you do that, you get a salt and water. Now here are some type problems that you might need to do. And we're going to start with non-math problems. But if I tell you, I want you to write a neutralization reaction to produce zinc chloride. Now, zinc chloride is the salt, and you're going to produce it. And the products of a neutralization reaction are going to be the salt and water. So if I tell you that the salt is zinc chloride, write that down as a product. That's what you're making. And then any neutralization reaction, you make water also. You need that so that you can balance the reaction, because a neutralization reaction requires the reaction between an acid and a base. So and it did, and I chose HCl because I chose HCl as a reactant because I needed an acid with chlorine as my negatively charged ion, because I've got to make zinc chloride. Then I needed a base that has zinc as its metal, okay, because I was making zinc chloride. So you could have chosen different things, although you probably would have had time to, in theory, there could have been other substances to choose, but you still would have had to make it work, whatever you chose, so that you would have a chloride cation, excuse me, a chloride anion and a zinc cation, okay? So there's not really a whole lot of options. Now, I do want you to notice this. Notice that I gave you the formula for the salt with the subscript of 2. Zinc is a transition metal. So you wouldn't know by looking at the periodic table what kind of ion it forms, but you do know because chloride is a -1, and you know from the formula that this means that zinc is 2+. All right, so zinc is 2+ because of the subscript, because chloride is always 1-. All right, so you have to write the formula correctly here, but that also means that helps you write the formula for the base, because zinc has a 2+ charge. That doesn't change during the reaction. It still has a 2+ charge. So you had to make the formula with the base, zinc hydroxide, with the subscript of 2 right there. Okay, because zinc is 2+, hydroxide is 1-. So you do have to remember some of those things from earlier in the year. Okay. Oh, I did not write this in my notes, but if you don't have forget the acid-base titration for just a second. If you don't have your textbook open, pause this video and go get your textbook. And now that you're back, open your textbook to page 425. And I want you to look with me at example 16-. Okay, it says, what salt is produced from the neutralization of barium hydroxide by acetic acid? And you're given the formula for acetic acid. Okay, so you have C2H3O2. Now the question you might say is, why is that one H out front? And then you have 3 other H's there in the middle. That's because this is the hydrogen that gets donated when acetic acid reacts. Okay, that's the hydrogen. Those other hydrogens don't get donated. So so when you write this, you separate out the one hydrogen that's willing to be donated and causes that to be an acid, and all those other 3 hydrogens stay tucked in there in the formula. Okay, so what salt is produced from the neutralization of barium hydroxide? So barium, if you look at the periodic table, it's in group 2, so it makes a 2+ ion. Hydroxide is always 1-. So in order to write that formula correctly, you have to write BaOH2. All right, and then you have acetic acid. Now you wouldn't have known to put the 2 there yet, but when you do that reaction, the hydrogen is donated, that front hydrogen from acetic acid is donated to the OH groups to make water. All right, and then barium, the positive ion from the base, joins up with the negative ion from the acid, and so you get barium acetate. And then you would look and you just have to go back and balance it to make sure all your atoms are accounted for. So you'd have to put a 2 in front of acetic acid and then a 2 in front of water. Okay. And we're going to start talking about acid-base titrations. So keep your book right there, because I want you to look at a picture of this. But an acid-base titration is a chemical process, quick chemical reaction, where you're trying to do a neutralization. And you do it so that you can determine the concentration of one of those substances that you don't know. And there's a titration curve, here's what it looks like. Okay, and the way this would work is you would use one of those indicators, and you would add, you'd have one type, an acid or base, in your container, and then you would slowly drip the other substance into that beaker. And as soon as there's a pH shift, you would stop. And then that would help you as you compare volumes to figure out the concentration of your unknown substance. Okay, so here is a titration curve, and they've used bromocresol green as one example, and then phenolphthalein as another. Those are just pH indicators. If we were in the lab, we would be doing a titration right now, and we would go through it, and I would explain how helpful it actually is to help you find the concentration of the unknown. What I will do on tomorrow's video, is actually show you another video of a titration so you can see how sometimes tedious a process that can be, because you don't want to dump in a whole bunch of substance, because then that throws your curve off greatly. But a few terms to know when it comes to titrations, and then we'll look at the mathematical equation you're going to use to solve some of these problems to figure out the concentration of your unknowns. But if you look at this curve in this particular titration, you'll see this term equivalence point. Well, equivalence sounds like equal. So the equivalence point is when in your mixture, you've reached equal amounts of hydronium ion and hydroxide ion. And the end point is the point where you detect the change in pH using whatever indicator you've chosen to use or you need to use. And there would be a reason to choose certain indicators. It depends on, if you go back and you remember looking at these charts, go back here, indicators change colors at different pHs. Some of them change while they're still very acidic, and some of them don't change until they're still quite basic. And so depending on what you're mixing together and which acids and bases you're using, that could dictate which indicator you would need to use. And that would be something you're going to learn along the way. It wouldn't be something I would ask you on a test, which indicator should you use. But just know that just certain substances would require one indicator over another, depending on where you expect the pH level to be when you reach the end point. So this should look a little bit familiar, this equation that we're going to use. It's really, think back to when we were talking about gases and pressure. The M1V1 equals M2V2. Same idea, same kind of ratios. So we're taking the molarity of our known substance times the volume of our known substance, and we're going to set that equal to the molarity of our unknown times the volume of our unknown. And this idea of the number of equivalents. What that means is, if you think about some of our formulas that we've used for these bases and acids, sometimes you have to use a subscript. Like in one of those last examples where we have barium hydroxide, BaOH2. All right, that subscript matters because that means you have double the hydroxide if, for example, you're mixing it with HCl. So for every one hydrogen ion that you're talking about, you're dealing with 2 hydroxide ions. So you have to use base equivalents, okay, and or numbers of equivalents, particularly bases you really have to pay attention to, sometimes acids as well, but we're going to look at some of those problems. And I think what I'm going to do is I'm going to stop here for today. I do want you to highlight, if you've printed out the notes or you're following along with your own notes as I'm talking, highlight this formula underline it if you're writing your notes, star it, whatever you can bring your attention to, because tomorrow we're gonna watch a video on titrations, and it'll just be a quick video, but you'll see how you just slowly add your substances. So we'll watch a video on titrations, and then we'll do some calculations that you would be doing if we had a titration in the lab. Okay, so I will stop here. Have a great day. Keep working hard. We're almost done.